before I get into details, let me remind everybody of a couple things. One is that the observable tab is R1 minus R2 times some rotation matrix times dotted into the source vector. So this is our observable. This is the baseline. This is the rotation that connects the Earth frame to the celestial frame, and then this is the source that we're looking at. And we build normal equations from this, from our observations, and we end up with a series of normal equations. The normal equations look like NA equals B. And this is what we want to estimate. And our observations go into here. It's the value of the observations. And the kind of observations go into here. And the formal solution to this is we just invert the normal equation and say A equals n to the minus 1b. Now, one of the things that we are often interested in is station positions. They'll tell you that you cannot estimate station position from VLBI. Why do I say that? Suppose that I have this station R1 and R2, and I add a constant position to it. So I say R1 goes to R1 plus delta R, and R2 goes to R2 plus delta R. Then R1 minus R2 stays the same. This doesn't change. So what this means is that if I have a network and I move it in space, then my delay stays the same. Does this make sense? So I have to put in some kind of extra knowledge about this. So this is one kind of constraint or one kind of issue I have, but I have another kind of issue, and that is that I can rotate the Earth and also rotate the sources at the same time. So if I'm trying to estimate both sources and positions, I can't do it. And related to that is, so here normally things I'm interested in are stations, EOP parameters, and sources. And if I'm interested in stations and EOP, I can rotate the reference frame, but then also have another rotation of the EOP. So I can't estimate them separately. I have to put in some kinds of constraints. We call them constraints. So that is like extra knowledge that we have. Now, the fact that I have this thing here where if I add a constant to the station positions, the delay stays the same. What that means is that the normal equation n is not invertible. I cannot find the inverse unless I add something. So what does it mean when an equation is not invertible? Normal matrix is not invertible. It means that I have some vector n, vector b, equals 0. Where this is not velocity, it's just some vector. And I have one vector for each of these symmetries. I call something a symmetry if it leaves the normal equation the same. So there's a trick, and the trick is that I change n, and I modify n to goes to some n plus some sum of v transpose. I'll put over some sigma squared. And these vectors here, v, are things that are eigenvalue vectors of the normal matrix that have eigenvalues 0. And some people would like to do these as pseudo-observations. What you're doing is you're putting in some knowledge, a priori knowledge, that about the situation. So let me give you an example, because this is sort of complicated. Suppose that I suppose that when my big estimate of parameters, I have x1 here, x, y, z for the first station, x, y, z for the second station, x, y, z, etc. for the third station. Then I could have bx will just equal 1, 0, 0, 1, 0, 0, 1, 0, 0, dot, dot, dot. So I put in a 1 for I have all these x's. Then I do the same sort of thing for by and bc. Now, if you go through the arithmetic, and I think I do it in the presentation, what this ends up doing is it's saying that the sum of the adjustments for delta x equals 0, and the sum of the adjustments for delta y equals 0, etc. in delta z. So this particular adjustment is called no net translation, NNT, no net translation. And what that says is that when you solve for your VLBI equation, when you solve for your positions, you are trying to align the position to get as closely as possible to some a priori reference. So, that's the NNT constraint. Another constraint we have is called NNR. This stands for no net rotation. And what this means is that when you're solving for the VLBI reference frame, the frame that you want has this little possible, there's no rotation with respect to some a priori. So some stations may be rotated one way, some stations may be rotated another way, but overall, there's no net rotation. So that's the main point. So some people think of this as putting in a pseudo observation, and the reason I say that is because when you make the normal equations normally, what you do is you have this n goes to, when you're building it up at a time, n goes to q transpose. But this is some observation. And so that's what you're doing here. If this doesn't make sense, think about it maybe. So, in my talk this morning, I'm going to be coming to this at the end of this. But I wanted you to know why we're doing it and what's the root of this. actually, before I do this, let me say that there's other ways of solving these constraints. And one thing is, when I first started in VLBI, we used to say fix some station. So we say we know this one station, and that will get rid of 3 degrees of constraints. So you say, I know the position of Fortaleza, and then all of your other measurements are with respect to Fortaleza. But if you want to get rid of the angular constraints, the rotation constraints, then you have to fix something else. So an alternative to this is fix the station. Two is fix up at another station. And 3 is fix the direction to another station. So how does this work is that I have this arbitrary network. So I'm saying, okay, I'm going to have this station fixed. And then I'm going to say, this thing I can still have it move all around like this. So I'm going to say, over here, I'm going to say it has to be at this position there. And then I'm going to fix the rotation about that. So that's these 3 things here. These 3 things here are another way of doing it. So you end up estimating fewer parameters, but then you sort of break this nice equations here, which are symmetric. Okay.
Good morning, sir.
Good morning. You going to set me up?
Thanks to you. The right orientation. It's that.
Yeah. You always have to try it 3 times.
Still on.
Okay, I want to start off with a website first.
Okay.
So we've seen this website before, IBSCC. The link to everything IBS. But I wanted to point you to a there's a link on IBSCC to something called IBS Law. And what this does is anytime you have a VLBI station, a VLBI session, it shows you what is happening at the current time. So here is session 2TP164, and you can see the VLBI antennas that are in the session. And you can see the schedule, the stuff that's green that has been observed. If I click on a source, it will give me an image of the source, so I can look at what the current source is being observed?
Excuse me, sir. The people asking for the full screen.
Full screen. Tell me how to do that.
Ah, okay.
They cannot see this?
So what are the red dots?
The red dots are antennas. Yeah.
So you said you click on the sheet.
This is a schedule right here.
Okay.
So, so that's like one of the sources. And the green is stuff that's been observed. The red is, I guess, what we're observing right now. And so this is sort of the fun thing to look at. It also has webcams of the stations that have webcams, so that you can see, if the webcams are active, you can see the stations move around. And this is a service of Bordeaux Observatory. And I guess that it sort of shows where the antennas are pointing to. Anyway, so this is a fun thing to look at sometimes. Okay, now I want to go to my first off, any other questions about this?
Teacher, what's the oldest what's the oldest data in live presentation?
Well, it only does it, I think it only does it for sessions that are happening right now. I'm not sure if you can do it for previous sessions or not. Okay.
Teacher, with the live presentation, you have the delay of the presentation or not?
With the IBS Live?
Yes.
That's happening in real time.
Okay.
So yeah, it's happening in real time. If we go back to it, it should say the current observation is 15:25, which is the current time in UTC. And this observation is observing for 266 seconds. So when it's done, we'll go to the next one. You can see that all the stations which are observing this. And this kind of session is a terrestrial reference frame session. The sessions that start with T are primarily for tying stations together, getting stuff for the terrestrial reference frame. Okay. So Max, I want to do this presentation.
Let's go.
Is it, people see it there online?
It's okay somehow? It's okay.
Okay.
Set.
So a lot of this stuff I've talked about previously. I just want to go through it again, and some of the stuff I've said verbally, but I want to have it in a presentation. So this is something I gave at the VLBI school last year. And here's my topics, getting data ready to use, etc. I'm going to discuss kinds of VLBI sessions, kinds of VLBI solutions. Yesterday we did some VLBI solutions, but today we're going to do some more different kinds. And then at the end, I'm going to talk about what I had up on the blackboard was degeneracies in the normal equations and how you solve it. So the data, the VLBI data, is stored in this Vigos DB format. And every step in the processing chain, you add new information to this. And each Vigos DB is a directory and a bunch of files. We saw this yesterday when we were choosing things, and we've seen it earlier. And you know, one thing, I came from theory. My background is in theoretical physics. And you know, in theory and reality are the same, but in reality they're different. And when you actually do something, it's different than you think it's going to be. You have predictions about when you take data, things should follow a normal distribution, and you shouldn't have outliers more than 3 sigma. But in reality, you do. So you have to do various stages along the way to get rid of bad data and figure out what to do because reality is messy. As I said yesterday, there are 4 stages in data processing, and people talk about the version 4 of Vigos DB. That's the one that's ready to use. And new solve is the last step in producing this data. So here are the steps. The correlator takes the data. Vigos DB calc adds in theoretical values. It adds in theoretical values for the station positions, the source positions, the EOP values, and this is based on sort of latest data. Vigos DB proc logs reads the log files and puts in net data and calibration data. And it also extracts other data that might be useful. And the new solve, which we played with a little bit yesterday, does the data editing and the ambiguity resolution and calibration. And then once you produce that, that is used by other scientists to do whatever they want to do. There are several institutions that are primarily responsible for producing version 4 of Vigos DB. They are NASA, USNO, and BKG. And BKG is the German Institute of Cartography. And so they are the ones that produce the version 4, and then everybody else can use these. Other institutions can produce version 4, and they do it, but they're sort of for internal use. Steps 1 through 3 can be done automatically. And we have scripts that do all of this. We have a job that looks at the cron job that looks at the correlator, looks at various places every 10 minutes or so, and if there's a Vigos DB file ready for the correlator, it picks it up. It looks at the log files. If they're ready, it picks them up, and then it does all of these things. And it will let the analysts know when it's ready for going to the next step. Analysts will look at this and will say, is there something wrong with, or are we missing some information? For example, has some station not submitted a log file? And if so, then somebody can call up to say, hey, you guys messed up with the log file. Please submit it. But we're trying to eliminate as much human stuff as possible. We started doing steps 1 through 3 automatically about 3 or 4 years ago. When we first did it, the analysts complained about it. They said, well, we've always done it this other way. It really doesn't save any time. Why are we doing this? And now they like it because they don't have to spend time doing this. each of these steps, 1 through 3, only takes 4 or 5 minutes, but that adds up. So NewSol takes, yes.
What's the size of the raw archive?
What's the size of what?
Of the raw archive.
Raw
File.
raw file. There are two different answers to that. One is the version 1 VigosDB is not that big. The file that goes into the version 1 is many, many gigabits. Gigabytes, so it can be like 300 gigabytes or something. And if you start with that, you can do many fancy things, but not many people do. That data is also available, but very few people use it. The VigosDB itself is not that much. The VigosDB for all the data we have is under 128 gigabytes. It all fits on this memory stick I gave you. So the stage in processing that takes human insight is NewSolve. And NewSolve is an iterative process. That means we start with a simple solution and then we make it more complicated, and then we throw away data at different stages. What we work with is the residual. And the residual is the difference between our measured and our modeled delay. And ideally, this residual should be about the size of the error in the measurement. And if it's not, then we need to adjust the model or do something. So here is a plot showing the residuals for one session. And you can see that most of the points fit the cluster pretty closely around the center line. The horizontal axis is in nanoseconds. And this is the residual for all group delays. And so this is sort of the output of NewSol. Now, geodetic field data comes in two flavors. There's SX, which we currently use, and there's Vigos, which we have started to use. And Vigos is more precise, and it uses these smaller antennas. And it has several advantages. One is that for SX, we have this group delay ambiguity, where we need to add numbers to get things to line up. And Vigos doesn't have that. And the reason SX has this group delay ambiguity is because we're only observing at small slices in the frequency. If we were observing continuously, there wouldn't be such a thing. And in SX observing, we get two bands from the correlator, and from these two bands, we estimate the ionosphere. In Vigos, we just get one group delay. The correlator estimates the ionosphere as part of the correlation process, and they don't provide that information. Yes?
In meters, how many meters that ambiguity represent? It's possible to say that proportional to one distance?
So in meters, 50 nanoseconds is about 16 meters.
You based on the position of the station, and show that ambiguity.
Yes.
You know how many.
Yeah. Yeah. And yeah, that's one of the things that goes into it. So yeah, when you're processing the data, sometimes you'll see things that will be on. You'll see this in a minute. The correlator will have some things on different lines, and then you need to line them up. But the correlator needs to know, when it's correlating stuff, where the station position is within an ambiguity and really much closer. So here is a chart showing the data at X band before we do ambiguity resolution, and you see that the data lines up on these different lines. And if you look up at the top, can't really see it there, but it says, is that going on? Up there it says 50 nanoseconds as spacing. So the way that you do ambiguity resolution is you start with a simple model, and then you are all of the residuals within an ambiguity. And if they are, then you're done. And if no, then you modify things, you add these values to the residuals so they are within an ambiguity. And here's what you have after you've done that ambiguity resolution. So things look much cleaner, but you see a pattern there. So what do you see?
Basically a straight line, but we have two diverging.
Yes, you have two diverging lines. And what you have is you have...
Teacher, I have a question. Those VLBI ambiguity have the same meaning as in GNSS?
What is VMSS? Yes, yes, absolutely. It's exactly the same thing. So you see these lines here that go, red line goes up like that, and then it stops, and then you have another red line that goes up like that. Or you have a blue line that goes down like that, and then it stops, and you have a blue line that goes like that. Anytime you see something like that, it's a sign of a clock break. And what that means is suddenly at some station, the clock jumped. And why do I have it going down some places and going up some places? These are plots of the delay. The delay is a baseline thing. So for some observations, for example, I might have 4 delays at the first station. And in other observations, 4 delays would be the second station. So depending on the sign of that, the clock is either added or subtracted. Does that make sense? So I see that. I see those lines like that. So that's like, as I said, a clock break. And when I have drifts at the masers, this causes a drift in the maser delay. So that's why I have that slope there overall. But there are other things that can do this too. You know, if we have these cables that bring down the signal, they get hot in the sun, and so they expand, and that's going to cause the cable length to change. But sometimes you have a discontinuity, and that's a clock. So here is looking at one of these stations, Mendocino, where I'm just looking at those baselines. I have a clock break right at the end. And what you do is you put in an extra parameter which solves for that clock break. So you say, at that point, I'm going to say the clock jumps, and I'm going to estimate it. And that's what it looks like after fixing the clock. So maybe, I hope that we can get a chance to go through and solve something that has one of these things. Sometimes you know what it causes a clock break, and sometimes you don't. All of these sites have signal that goes out called 1 PPS, which means 1 pulse per second. And that's supposed to sync all the electrons. So occasionally, the maser will sync to the wrong pulse. You'll have a jump in the clock of 1 second, which is huge. There used to be a station in Australia that would have frequent clock breaks, and we didn't really understand why, but it turned out that every time they turned on their air conditioning, there was a clock break. So And the air conditioning go on and off, so you'd have like 10 clock breaks in a session. Ionosphere. We talked about this yesterday, and that when the signal goes through the ionosphere, it is delayed. And this introduces a change in the group delay. And this is frequency dependent. So by doing this linear combination, you can come up with something called the frequency independent, the ionosphere independent delay. So that's why in VLBI we exhibit two frequencies. And they do the same thing in GNSS. They exhibit L1 and L2, and then take the difference between the two to get the ionosphere free delay. So once we have done all this stuff, we've done the ambiguity resolution, we fixed the clock breaks, we've applied ionosphere correction. It could still be that their points don't fit well. And the term for these is outliers. And these should be estimated because they can cause problems with the solution if they're not. So there's a couple of ways to do this. You can just pick these points by hand, or you can use another criteria. The criteria that we usually use is 3 sigma. That if you look at the uncertainties of the points, that's sigma. And if the points are 3 sigma away from the line, then we throw them away. And we don't really throw the data away. We just set a flag saying, I don't think we should use this data. So let me go back to talk about this a little bit.
What's the difference of CAL and KNGS in USOL files?
Let me see it. Oh, CAL and NGS?
Yes.
Is that your question or somebody else's question? The KL has all of the data. The KNGS has just some of the data.
Okay.
Good. Okay, so now I'm going to go, after we're done with the new SOL, going to talk about modeling the data and doing solutions. So here's this equation that we've seen a lot of times. We've seen this is just the geometric delay. And the geometric delay depends on the station positions. It depends on the orientation of the Earth with respect to the celestial reference frame. And it depends on the source that you're looking at. But really, there's a lot of other stuff on here. And Jean-Pierre talked about this last Friday. I talked about this last Friday. And so we'll briefly talk about some of this because we covered this before. These remaining pieces here, some of it is modeled. So you have a good idea of what it is. Some of it you measure. And then some of it you have to estimate. So things that we model are general relativity, Earth tides, loading effects, antenna deformation, the a priori delay. Now, I've used the word a priori a lot, and I realize I probably haven't defined it. Does anybody know do you know what it is? Yeah.
Or, like, you see that.
So a priori means your starting assumptions, your prior assumptions. So the a priori information is, we say, this is how much atmosphere we know about. Then we want to estimate what's left over. Or the a priori station position is, this is where we say, think the station is right now. And then we're going to estimate adjustments to this. And all of these things, all these models here, are continuously improving over time. And there's probably still more work to be done. The general relativity model is currently thought to be good at like the 2 picosecond level. The new model is coming out, which is going to be good at like the 0.1 picosecond. Earth tides is pretty well known. Ocean loading, you have to have models of the ocean and how deep things are, etc. There's probably room for improvement there. You have pressure loading. To calculate that, we use results from numerical weather models. And there are different numerical weather models, and they give slightly different answers.
Teacher, in a priori options, why the source exploratory model in default is disabled?
By the way,
In default is disabled source of the exploratory.
source structure model.
Yes,
That's because for most sources we don't have good models.
because the hardware, right?
No,
No.
it's because we don't have good models for most
Oh, okay.
sources. So what was this? Where was I? Okay. Okay, so pressure loading, we have these various models for that. I should mention that VLBI routinely applies these loading corrections. The other techniques like GPS and SLR do not. So when you're comparing VLBI and SLR stuff, you need to take out the pressure loading corrections. Cable calibration is one of the things that we can measure. And we do this by sending a signal that goes from the bottom of the antenna up to the top and bounces back. And so we can measure cable cal, and that's one of the things that's recorded in the field system, the log. And the cable cal delay is removed from the observer. There's some stations where we know that there's problems with the cable cal instrument, and so we don't use it. Thermal expansion. Antennas expand and contract, and there's two effects to this. One is within a day, but then there's seasonal effects. There are some antennas where the difference between the seasons is 50 or 60 degrees centigrade, which can cause a large effect. And this will primarily cause the antenna to move up or down. So if you didn't accommodate for this and you measured it, you say, the position is moving up and down.
The expansion of the plate because of the heat is a big factor, or just the height?
It's mostly just the height of the antenna. And this is modeled based on what the composition of the antenna is. Is it aluminum? Is it steel? And then you also have whether the concrete pad, what the concrete pad is. There is some concern about, not concern, but when the sun heats something, it doesn't heat up instantaneously. There's a lag. It takes a while for things to heat up. So you have to put in a lag of like 6 hours. So this lag is useful for like daily measurements, but it doesn't really matter if you're comparing an antenna in January and in May. And here are the things that we estimate. We estimate the atmosphere, the residual atmosphere, we estimate clock variation, and we estimate baseline clock.
The cable cal means we're using a pulse because the graphing is up, going up.
Yeah, I don't know the details, but there's a pulse that goes up the cable and comes back down, and then you see how much that pulse shifts.
Because the delay, right?
Yeah, because of the delay. So we estimate in atmosphere, this is the difference from the a priori. We estimate clock variation. We estimate baseline clocks. And these are called nuisance parameters because most of the time we don't care what these are. These are just getting in the way of what we are. I should mention that there are some people who are estimated in the atmosphere. That in GPS, they also have to estimate the atmosphere. And the GPS estimates of the atmosphere go into the numerical weather models because that provides additional information. So everything we estimate, we can decompose it in two parts. One is some function of the time, and the other is some geometric term. And this is useful because when you're building your software, you can build software for the geometric term and then use common subroutines for the time term. Now, when we first built Solve, we didn't really realize this, so everything is mixed together. But in the more modern things, it separates stuff. So in terms of the time, there are different ways of doing it. You can do it as a polynomial. You can do it as a harmonic. You can do it as step functions, piecewise linear, whatever you want to do. Usually what we do is, the more modern thing is piecewise linear functions. Now, when we go through the atmosphere, we model the atmosphere as several streams. We have the a priori, which is calculated. Then we have the zenith atmosphere times some mapping function. The mapping function depends on the elevation. And then we have other terms called gradient terms. And the gradient terms are due to the fact that the atmosphere looks different if I look in this direction than if I look in that direction. And you can imagine that if you're at the coast, like at Fortaleza, if you look in one direction, the atmosphere looks different than the other direction because you have more water vapor. So the gradient terms are used to model. And the a priori atmosphere is derived from local metadata, which is what we used to use, or numerical weather models, which is what we mostly use now. The current mapping function we use is provided by the Technical University of Vienna, and they calculate a mapping function at every 6 hours and based on numerical weather models, and this is updated once a day. So we download this model and we use it in our analysis. We usually don't use this when we're processing intensive data because there's a lag. We usually get the data from the ULBI segments before we get the data from the Technical University of Vienna. And here's what the residual atmosphere looks like for a station. So there is a delay. It causes variation of the delay of up to 300 picoseconds in the zenith direction. Clocks I've talked about. If I have a time difference in the time tags, this will cause an apparent delay, and this is called a clock. And we model this as a polynomial plus a piecewise linear term. And this is caused by a frequency shift of signals. I want to mention that all of the techniques, all the space geodesy techniques, have the same things. They all estimate clock polynomials. GPS does this, SLR does this, etc. So this is common. And here's what the clock variation looks like. Typically not as big as the atmosphere. If I see sometimes I'll see a big rate. And if I do, that means that the hydrogen maser is drifting at some station. And the drift of the hydrogen maser is measured like every day, and then it's adjusted if it gets out of whack. Do you have any comments about that, Adialdo?
I see on the relation reports that almost station has a small drift on their mix. So it sounds like that's not a big problem for dynamics.
Small drifts are not a problem.
But do you wish that all the stations have no grid or at least as minimal as possible?
Yeah. Yeah.
Yani bozuk.
Some of it's temperature. I'm not sure of all the details. What causes everything?
Teacher, what is that zero jumps in the gravity?
Why those narrow jumps?
Yes.
It's just where we don't have data. for some
Oh,
period of time.
lost data.
Yeah. Well, we may not just schedule something there. So this has a point for every observation that we've taken, and we don't take observations uniformly. So now we come to something that nobody really likes, and this is called baseline clocks. Now, earlier, I think yesterday, I talked about how if I have the closure around the baseline, it should sum to 0. And sometimes it doesn't. And one of the reasons it won't is that you have missing channels. In SX, you observe at some set of 16 channels. And if one station is missing some of those channels, sometimes it will cause a change in the delay. So when you do that, if I have a sum around triangle, it does not sum to 0. So what we add in is we add in this term, which we assume is constant over the session. This is called a baseline clock. So in the analysis, you'll first estimate without baseline clocks, then you'll turn on baseline clocks, and you'll see if they're significant, and if so, you'll keep them. Modeling the delay. So here I go through the process of setting up the normal equations again, as we have some observations, and then we have the calculated values on the right-hand side, and then we have adjustments, and we want to estimate the delta P. So the red term is what we want to adjust. We want to estimate. The blue terms are the partials, and you can rewrite this as this matrix equation. So this is sort of standard. So you have observed minus calculated plus this other term. And I rewrite it as this way. The slang term people will say is they'll say O minus C. Now, in general, we know that our measurements aren't perfect, so we have noise. And so the O minus C is this linear function of our estimated parameters plus some noise. And our goal is to find this estimated parameters. So there's lots of ways of solving this. There's lots of ways of estimating what this thing is. Musolf has a couple of ways of doing it. One is called a square root information filter. Another is a Kalman filter. Has anybody heard about a Kalman filter? So, and we're going to use least squares. Now, a Kalman filter and least squares are the same under some circumstances. So, what a Kalman filter is it's a way of updating least squares equation one observation at a time. And I'm going to use least squares because it's easy to understand. And for each of these, there are lots and lots of books and articles about this. So I want a solution to this. I assume that I have this covariance matrix here. So what this is saying is that different observations are not correlated with each other. That's what that delta JK means. It means that one observation is independent of another. And then I form this chi-square. Now, this assumption that one observation is independent of another is not really true, but it's an approximation. So why do I say this is not really true? One example is suppose that I look at the atmosphere here, then I look someplace else, and then I come back. Now, I'm looking at the same atmosphere, so I'm just looking at it a couple of minutes later. So if there's like some clump of stuff happening up here, I'm going to see it both times. But for simplicity, it's easiest to assume that things are independent. So then I make this chi-squared over here, and I minimize it. Now, the person that first came up with this was Euler. And he came up with this to estimate orbits of planets back 200 years ago. He used this technique. By comparing observations to theory, he was able to get better estimates of the planets. Okay, so here I say, usually we deal with reduced chi-squared, and here's the definition of it. And this parameter here is the residual. And ideally, the residual should be about the size of the error. So you'd expect this thing to be right over the 1. So we just go through using calculus, and we build up the normal equation here. And then we build up the b vector there, and we have this solution. And this is what we invert. So a couple of comments about this. One is that if I look at the normal equation, the more observations I have, the bigger it is. And also it depends on the uncertainty of the observations. So if I have observations which are better, it's also going to be bigger. So that means that the uncertainty in my estimates depend on the uncertainty in my observation divided by the square root of the number of observations. So if I want to have better estimates, there are two ways of doing it. One is have more precise measurements. The other is take more observations. Now, when we actually do the calculation, what we find is that our chi-squared is not equal to 1. It differs from 1, and it's usually about 2 to 4, something like that. And what this means is either our model is wrong or our estimates of the noise are wrong. And our standard, and to get chi-squared equals 1, what we end up doing is we put an extra noise in the observations. And we add the extra noise so that our chi-squared eventually equals 1. Now, why should our estimate of the noise be wrong? Well, the estimate of the noise that we use depends on just its thermal noise. So it's like what the uncertainty is of a given observation. But it doesn't take into the fact that there are other sources of error. So let me give you an example. Suppose I have I'm measuring something with a ruler, and the ruler has markings of 1/10 of a millimeter or something like that. I look at that and say, okay, so that's my uncertainty. Now, if the antenna is heating, then it will maybe expand or something. So there's other sources of error which I'm not accounting for. So one of the sources, the dominant source of error is thought to be, or the two dominant sources are thought to be atmosphere and source modeling. So when we're propagating through the atmosphere, we're not modeling it correctly. Sources are not point-like objects. So we add in extra noise. This is called reweighting. Again, this is something that everybody does. It's it's like a convention. It's like, yeah. I don't know if you have this saying in Spanish, but in English we have the saying, sweeping the dirt under the rug. So that means, you're hiding it someplace. So, we're hiding the fact that we don't know things. So, and there are different ways of doing it. One is you just add the same amount of noise to all observations. Another is you say, my noise depends on the station. So I figure out, so for each station I add some amount of noise, and it depends on the station. And that sort of makes sense because you can think of things being station dependent. And then the last is I add it depending on the baseline. This is, my recommendation is that you add something depending on the elevation of the observation at each site. And the reason for this is, as I said, most of the error is due to the atmosphere modeling, and the atmosphere modeling gets worse as you go to low elevations. And you can show that if you use this, you improve your estimates in various ways. Now, I say 10 picoseconds there, but really, that is station dependent. So here is a chart showing what the atmosphere looks like. And I have each antenna is looking through the atmosphere, and there are these clumps of stuff going through the atmosphere. And the antennas see different sorts of things. And these clumps cause changes in the delay. So I'll just leave that because okay. So when we're modeling stuff, what we estimate depends on two things. One is it depends on the kind of data we're taking. Partly it depends on what we're interested in, station position, sources, EOP. It also depends on how much data we're taking. If I need to have enough data so that I can estimate the parameters. If I have n observations, I can estimate at most n parameters. If I have a straight line, I need to have at least 2 points. Ideally, you want more than that. So ideally, I'd say you want at least double the number of observations as you do parameters. If I'm estimating something like, well, I'll get to this in a second. So if we don't estimate a parameter, what we have to do is we have to hold it fixed. No.
No?
No, air traffic does not create problems that we see. So if we can't estimate parameters, we hold it fixed and estimate the others. When I say we hold it fixed, what does that mean? It means we get the values from someplace else. So we have 3 kinds of VLBI solutions that we're generally interested in. One is an EOP solution. And there are 2 of these. There are intensives and rapids. And the intensives are 1-hour solutions that happen every day. And we measure them every day because EOP changes. And we need to be able to measure it quickly. The rapids happen twice a week on Tuesdays and on Mondays and on Thursdays. And these sessions take about 2 weeks to process. The intensives are processed in under a day. Then there are terrestrial reference frame solutions. And these are either global, where we have stations all over the world, or we have local networks. It's like the European VLBI groups have sessions just focused on Europe. Japan has just sessions focused on Japan. And then we have CRF, celestial reference frame solutions, which are to estimate the station, the source positions. So here I talk about the special EOP solutions. Here, when I say the data is ready and analyzed in 1 to 3 days, now I'd say it's pretty much analyzed in a day. And here are the 24-hour solutions. Here's the other kinds of solutions, the celestial reference frame solutions. Here the network size varies. They run as stations are available. And it's not really, you don't worry about how long it takes to process the data because the sources aren't going to change their position. And for the terrestrial reference frame, it's the same sort of thing. So we'll have roughly a dozen or 2 dozen of each of these. So here's this example of this intensive session with Coquet-Betzel. This is the first intensive session that we started to do. See, it has a long east-west baseline, which means that it is sensitive to rotations about the z-axis. So when we're doing the intensives, we assume that we know everything except for a few parameters. One is UT1, and then we estimate clocks and we estimate atmospheres. So here is what the parameterization looks like. So here's the clock parameter, and here's the UT1 parameter. Here's the clock parameters at Betzel. And here's the atmosphere parameters at Betzel and at Cook. And I have this minus sign there because Cook is the second station of the basin. And if we wanted to estimate atmospheric rates in episode. Yes.
I noticed that we use a lot of Cook and West. We use them because they are so far away. That it's
So those are the those are the intensives that are used. They're measured. Those are measured 5 times a week. But there are other intensive baselines as well. Let me go. There's another baseline that goes from Europe to Japan. So that's frequently used. That baseline there. It's not quite as long. People are also looking at baselines that go from Europe to Texas. But that's a good long baseline.
If the start of the first we always Cook and West.
Yeah, that's because I've done a lot of presentations on it, so it's easier to just use slides.
Professor, so if you want a more detailed observation, if you use a more station, the station prepared for the best observation, use the Japan or station to make a triangle, triangle.
Yeah, if you had a triangle, you could measure all the components of EOP. With just a line like that, you can only measure one component of EOP.
Use 8 stations, you make a lot of triangles, and you say, the name, you interferometry of 2 and 2 stations to calculate baseline interferometry above that.
If you have more stations, you get more information. Okay, let me continue.
How many data are generated in intensive or intensive observation?
In an intensive session, you typically have like 20 to 60 observations. So one of the things about intensives is that since you're only estimating a few parameters, the parameters that you don't estimate can cause errors in the intensives. If the station positions are wrong, this will cause an error in your measurement. If the EOP is a priori EOP for the other components is wrong, this will cause a problem. And we had an issue with this when there was an earthquake in Japan. And so one of the stations that we used in the intensive position changed. And so that caused us errors in our UT1 estimates. And we had to fix it. Let's see. We just have about 10 more minutes left, and then we'll have our coffee break.
Okay.
So for 24-hour sessions, we estimate the zenith of light for the atmosphere. So we have an offset and a rate and a piecewise linear function. We estimate atmospheric radiance. We estimate clocks. And if we're interested in EOP, then we estimate EOP. So if you go through the arithmetic, this is the number of parameters we're estimating. 5 times 114 times the number of stations. And here I'm assuming that we have 10 stations. Nowadays, we typically have like 14 stations. So we're estimating 1,000 or 1,500 parameters. And really, these are the things that we're primarily interested in. So we're estimating 1,000 parameters, but really all we are interested in is a 5.
So, what is node X, node Y?
That's nutation. So that's we talked about precession nutation, where that's the Earth's spin axis location in space. Okay, I'm going to stop here. We'll have a break. My voice is getting tired, and then we'll continue. So back in 20 minutes. morning, I started off by showing this website, IBSLI. And this shows anytime there's a VLBI session, it shows what is happening right now. So I have this map here of the VLBI session and all the stations that are involved. And the observations. So basically, I just wanted you guys to be aware of this. It's sort of a fun site to look at. There is webcams for the different sites. If the webcams are active, you can see what they're doing. Do you have a webcam at Fortaleza?
No.
And what else is there? And if you click on a source at a particular time, it'll give you whatever information they have about a source. Sometimes it's just a picture like that.
So who takes care of this website?
This is University of Bordeaux, or Bordeaux Observatory.
So who can help us on configuring a camera for integrate with that?
Buy a camera, communicate with them. They'll help you, I guess. We have a camera at NASA. I'm not sure if that's hooked up to it or not for GGO. The one other thing I wanted to talk about was, before we get back to this.
Excuse me, sir. I have a question.
Okay. No, the ionosphere combination, so there's 3 questions. One says, does the ionosphere combination remove the ambiguities? And the answer is no, it does not. So you need to remove the ambiguities before you do the ionosphere combination. That shouldn't be a problem because the ionosphere correction is smaller than an ambiguity. So he also says there's a map from JPL that has RMS error up to 6 TEC units. How much is that? And I don't know off the top of my head. I can look that up. We can also see what the typical size of the ionosphere units are. I had this equation up there that had the correction of the ionosphere was proportional to 1 over the frequency squared times the TEC times a constant. And the constant is something like 10 to the minus 14. So it's very small. And the last thing is the quality of the derived ionosphere sufficient for VLBI? My answer is, if you don't have anything else, it's better than nothing. But radio astronomers who observe at a single frequency will sometimes use that. So that answers those questions. Adioldo had a question the other day about, I think it was you, about how long, or maybe it was on here, about how long should stations observe if you bring up a new station?
2 years.
I said 2 years, and I looked up here. That's not it. Wrong thing. I just went back there. I really like this. Overlap operations. On the IBS website, there's something about no overlapping operations. And there's this little line here. It says they'd like a minimum of 18 months with at least 1 observation a month. So, 2 years is good if you observe frequently. And the reason is because you want to make sure that your velocity of the 2 solutions is consistent. Okay. let's go back to the presentation I was doing this morning, and I'll finish it up. Okay, Max,
Okay.
I need your magic.
Okay. I do that. Okay. Window. Okay, got it.
So let me just talk a little bit about the next 2 days. So on Friday, not Friday, tomorrow, we're having a presentation on EOP. And let's do it after the coffee.
Okay.
Okay?
The morning or
In the morning. That way you can be free. And on Friday, and tomorrow is also Jean-Pierre's birthday, so we should wish him a happy birthday tomorrow. Yeah, his birthday.
So,
And yes. And Friday, it's Eric's birthday. Anybody else's birthday?
No.
Maybe we should bring in a birthday cake. Okay, so I'm going to finish up this talk here, and then we'll see if we end for lunch after this or not. So from a single session, I can estimate the station positions, or I can estimate the source positions. And that is useful under some circumstances. And it's useful if you have a new station and you want to estimate its position initially so that you can use that position going forward. So whenever we have a new station, we estimate the position, then we use that as the a priori going forward. The same thing happens with if we have a new source. We'll take observation of the source, and then we'll estimate the source position, and then we'll use that going forward. It's better if you combine the data from several sessions. And sometimes if you have, this is more important with sources, but sometimes if you have a single session, and I told you that you had to introduce ambiguities. Well, you start off with some estimate for the source position, and you introduce ambiguities, and it could be that your source position is wrong. And then once you get more observations in other sessions, you may have to go back and fix things. So as I said, the real strength combines in a combining session, and we have something like 7,000 or 8,000 sessions from the beginning of the LBI, 24-hour sessions. Okay, why isn't this okay? Independent solutions are just a single solution or a group of solutions that you are processing independently. And you use these for EOP every time we get in a EOP session, we process it independently, or you want some preliminary results. And then global solutions are when you want more precise data.
Immediately would be involved in what we communicate.
So for the EOP, for the intensives, these are the short 1-hour sessions. The data is usually ready in less than a day. It used to be that it would take a few days to get that data because it had to be shipped manually. Nowadays, it's shipped electronically, and it arrives at the correlator in less than an hour after that. It's processed by the correlator, and then it's picked up and processed at the analysis centers. So the global solutions are used to get better station and source position. They're also used to tie the different networks together, in that not all of the stations observe at the same time. So you have, Fortaleza will observe in some networks at one time, some networks at another time. And then when I do this global solution, I get something that ties everything together. And one of the issues you have is that when you do these global solutions, you end up having really, really big matrices. And we use a technique which we borrowed from orbit determination back in the 1980s. And when they're doing orbit determination, they will break the parameters into two parts. One is a global parameter, and that is something that's a parameter that's valid for a long period of time. And then there are local parameters or arc parameters, and these are things that are valid for only a short period of time. And an example for that is that I'm estimating the atmosphere at a station, and that's only for this one day. Whereas the station position, I'm estimating it over a long period of time. So the station positions are a global parameter, and the local parameters or the arc parameters are things that are only good for a day. Another example is EOP. EOP changes every day, so I have to have an independent estimate. So when I make my normal equations, it looks something like this. I have a block diagonal structure where I have global parameters up in the top, right-hand corner, and then in the bottom diagonal, I have just the local parameters. Then I have coupling between the two. And then I partition my quantities into the global parameters and into the arc parameters. So the AG is the global parameters, station positions, velocities, and the A parameters are the arc parameters. So this is what a single session looks like. If I combine, say, 4 sessions, then I have a matrix that looks like this. So I have this global parameter at the top, and then I have this diagonal term, which is just all the local things. And then on the off diagonals, I have couplings between the global and the local parameters. And one the important factor here is that there's no coupling between the arc parameters on one day and on another day. Yes.
Professor, in last day, os Solve have a file to termination arc. Is that arc?
It's Sergey uses arc in slightly different way.
Oh, okay.
Yeah, slightly different. Okay, so this is the normal equation for 4 sessions. Imagine if I had this for a 7,000 sessions, it would just be huge, because each of those things like N11, that's like 1,000 parameters. So if I have a single session and I have 1,000 parameters, matrix inversion, I can do it in under a second. But matrix inversion grows like n cubed. So if I had 4 sessions instead of 1 second, it would take 64 seconds. If I had the whole guide data set, it'd be longer than human civilization to invert it.
So it's not a sparse market.
It is sparse because I have a lot of zeros there.
Let's see, those are blocks, matrix blocks.
Yes.
Matrix. What medium for 1 million by 1 million?
This is more like 7 million by 7 million. Or anyway, it's, I'm doing the arithmetic right.
I mean, this sparsity goes away very fast. You
But-
have algorithms to sparse.
Well, there is a technique, and there's a technique, and here I go through the arithmetic about how you do it so that you could eliminate the local parameters. And this is a technique called squeezing out. So you squeeze out the local parameters, and you just have this linear algebra, and then you solve this, and you end up building the normal equations going forward, and just end up solving for just the global parameters at the end, and then going backwards. And this technique is called arc parameter elimination. There was a paper about it back 30 years ago or so. But this is how we do this. So here's just, I talk about it for each arc. We calculate the contribution to the global part of it. And then at the very end, we invert it and then we go backwards.
Who are one of the developers of the algorithm?
I was not. I mean, the algorithm, as I said, was originally developed in the orbit determination community, but then it was coded by Ed Himwich into Solve. And one of the things I started off talking this morning about was symmetries and degeneracies in the normal equations. And the issue here is that if you just write down the naive normal equations, you cannot invert them. They have degeneracies, and the reason is because our observable has degeneracies. Our observable is the delay, which is the difference in arrival time at two antennas. And if I shift the positions of the antennas, the delay stays the same, which means that I cannot estimate the absolute position of something. I just estimate sort of the whole network. And to fix this, I have to impose some kinds of constraints on it. So really, in BLBI, I have a family of solutions to the normal equations, and I'm picking some particular solution. So, one of the things is I have this network here, and then I can translate it any place. And my BLBI equation can be exactly the same. So I have to pick out which of these positions do I want it to be in, which is the correct network. And the answer is that I say I want this network to be as close as possible to some a priori network. And the a priori network is, we use like ITRF 2020. So does anybody know about Noether's theorem? Noether's theorem here?
Yes.
So this is really,
Associated with conservation laws.
yeah, so this is, so here I go through this. We have our BLBI observable, and we have something that keeps the observable unchanged. So I have a translation. So that's one thing. You can also have a rotation. So I can rotate the frame, rotate the BLBI observable, and then also change the EOP. And I can do the same thing for the CRF. And so I say, I'm going to call these things symmetries because they leave stuff unchanged. Now I come from physics, and in physics, symmetries are a big deal. And so my claim is that for each symmetry you have, there is an eigenvector of the normal matrix with eigenvalue 0. And this means you cannot invert the normal matrix. And so then I say, there's a one parameter family of solutions based on each symmetry. And if I add in this other stuff here, that's if I have one solution, I can get another solution by just adding in this thing. So how do we estimate this? Well, we can impose constraints. And there are different ways of doing this. If we fix station and sources, then we can estimate EOP. There's no problem there. Fix stations in EOP, so we can estimate sources. Or we can do some mixture of fixing some things and others. And the problem with this is that you're treating some parameters specially. The way we used to do things when I first started was we would fix the station position and say this station, we know the position, and then we know an up component in another position and a vector to another position. And that is effectively the same thing. But what this means is then we know the uncertainty of this station exactly and everything else varies.
I would think that using a fixed star would be the starting point.
Big star?
Yes.
You could do that too.
Well, easier than to just suppose that this is a fixed station instead of that as a fixed star.
Or you have to have a fixed star, you have to have a fixed station too, because you have this rotation matrix.
In order to impose the constraint, the main constraint would be that's a fixed star, the main constraint.
Have to
Then
fix it.
we do the calculation and we correct the position of the station or the fixed.
You have to have more than one star fixed. You have to have several things fixed.
Polaris.
Anyway, so the constraints we apply are, they're called no net rotation and no net translation constraints. So this means that we have some a priori, and our network is as close as possible to the a priori. Mathematically, that means that if we sum up all of the adjustments that we make, the adjustments sum to 0. And the same with the rotation. For the sources for a celestial reference frame, we have this a priori reference frame. We say there's no net rotation with respect to that. So we have this international celestial reference frame. And that is what serves as our reference for which we orient or we nail our observations to. So here's just an example of how we do this. If I have a normal equation and then my station positions are the first components, then I want to impose a constraint on the x component. So I make that vector Cx, which has 1, 0, 0, 1, 0, 0, 1, 0, 0. Ones are where all the x's are. I do the same thing for cy and say z. And then I modify the normal equation by putting in that value there. And that removes the degeneracy. And well, I'm going to skip that. So one way of looking at this is that you're incorporating a priori information. And you're incorporating a priori information about your network. So I have in the top, I'm incorporating a priori information about, say, the station position. And I can modify not only the normal matrix, but the B vector, the normal vector. Usually we just assume that's 0. But I could say, instead of having no net translation, I want my network to be plus 5 centimeters. And I would do that by modifying the B. Now, sometimes our normal equations will invert, but the data is weak. And it almost doesn't invert. And in this case, we can put in constraints to make it a little bit stronger. And when we put the constraints in, we try to put in weak constraints, or enough to make it invert, but not enough to influence the parameters that we're interested in. Okay, so that's it in terms of this presentation. I guess we could start doing a little bit, we can maybe start doing some solutions using salt. So yesterday we did some independent solutions. Today we can start doing some dependent solutions. So get your computers and boot up into Linux.
Okay.
Any questions before I stop?
I can use delta of chronicle in that matrix.
I'm not sure what the question is.
I can use tensor notation with that matrix.
Yeah, sure. Yeah. Are you wanting to set this up?
Yes.
Okay.
Excuse me, sir.
So once you guys get your computers, I want you to open two terminal windows.
Okay, stream. 5. So is that because the tensor we calculated an S and R generate it's all set.
Okay.
Ah. What's I have another link.
guys are too happy.
All set.
So how do I minimize this?
Ah, you need
I need to turn off the.
like a Mac.
Okay, can they see it there? I need to do screen mirroring or something.
Loading. Let's do that. Work it.
Okay, guys. So I want you to open up two windows. At least start with two windows. And let me know when you're ready. Start the seashell in each of the windows, CSH.
Both.
We're going to use both. We may even go to 3 windows. In fact, open up a third window.
Ctrl plus Alt plus T.
In all of the windows, we want to set up the solve environment variables. So and let me know when that's all done.
Hold on.
So let's change directory to the examples solve directory. Change directory examples solve.
Alt.
So let me know when you're ready, Max.
Make now, right?
Pardon?
Set to system.cs.
Source, SGP,
Okay.
yeah.
Make it now, right?
And then change directory to the examples window. CD examples, yep. CD examples solve. CD examples, and then you can do CD solve.
Okay.
And it should tell you which directory it is in. Mine says solve, if I look at the prompt.
Example solve.
Yeah.
Next.
Is everybody ready?
Yes.
After examples, I need to put CD solve.
Yeah. If you type in a directory listing, you should see something like this when you're in the solve directory.
Yes. ARC files and C and TIFF files.
Yeah.
When I put solve, it didn't show this count.
You need to do ls.
So, Eric, type PWD. What does it say?
PW. O que apareceu?
It show examples that
Okay, so you're in the right area.
Okay.
So we're going to start by redoing one of the sessions we did yesterday. And so what I want you to do is type in enter E1 BL INDEP NMF.CNT.
Okay.
E1, yeah, it's BL underline INDEP underline NMF.
Pessoal, utiliza o tab que ele vai completando o argumento.
So that's what we did. That's one of the sessions we ran yesterday. And I'm going to rerun it just to get everybody to do that. Let me know when you're ready to hit enter on that.
It's loading.
Okay.
Oh, another file.
Do you have it going yet?
Professor, in another shells, put the sample folder, right?
So have you got that command ready? No, too slow.
Finish.
I never know if I am doing something. Say, no.
It should be E-L. Oh, sorry, E1. I was wrong.
Okay.
Yeah, sorry, I misspoke. It's enter E1, not EL.
Teacher, in another shells, open E2, we have in that, we have one, right?
No, we're going to do that in a minute.
Okay.
So once you do that, in another, once you've started that going, in another shell, type tail underscore work dir PRGF E1. So start the first one going. And then if you start this one going,
E1.
yes, you type
Okay.
tail minus F underscore workdir PRGF E1.
Got it.
Could you momentarily expand the window you're working on?
So in one window, what I'm doing is I'm running solve. And in the other window, I'm looking at some output that it's doing. And in the window that I'm running solve, it's just doing stuff. But in the second window, it's putting out its progress. So that's the whole idea here, is that you can, I'm going to go back to this first window. We're going to start running solve. Let me get out of this here. So I'm start solve running here. And then in the second window, solve writes a progress file saying each arc that it's doing. And so I can use that to see how far along I am in my solution. And for a short session like this with just 15 sessions, it's not that important. But if I have something that has like 7,000 sessions, I may want to see where I am.
56 seconds.
And for each of these things, it tells me which run it's done and how long it takes, etc. But the other thing I can do is I can run several runs of solve at the same time in different windows. So yesterday, we ran one run of solve, and then we did some analysis, and then we ran another run of solve, and we did analysis. But I can run, 3 or 4 runs of solve at the same time. And I'm only limited by my CPU. So Eric and company, were you able to get this going or not?
Solve is that the right window where what you did, I lost.
Okay, so you have another window where you also had are in the C shell.
I put the command the solve for E1. I did that in both windows.
Okay, so on the second window, is solve still running, or it shouldn't be running, right? It's running on one window, but not in the other.
The E1, yeah.
Oh. Okay, so the format the request is what's comment show the stage of the song, right?
Yeah.
I can see is
Bring
it's style.
your computer here.
Tail.
This goes with other video. I do. This is so and this I.
Okay, that's fine. So is this thing still going or not? Okay. So here what we're going to do is tail, and then
You can't see from.
I know. Worcester.
Eu posso organizar.
Ele tá colocando no meio, aí eu mostro.
So if I do this tail, it will just tell me, it just lists the end of the
Deixa eu
file.
ver qual é.
Okay?
Não, tail,
But
cifrão, work,
if I start this one going,
underline word,
okay, suppose I do tail here. It just says one thing there, and it's 2. If I change this to say tail minus F, it prints what's happening all the time. So it's all this processing over here, and then it's telling you there what session of it's what.
Okay.
So could you explain that to your friends? And
Ou asking for the shell. Better?
Okay. Yeah. No, it's not how I feel. You just
So
uh-huh.
the word digging is not safe. What's
You have your computer? Just bring it here.
so this working this
Uh, okay, so here, the environment variable profile setup. So CSA, yeah, you need to do it in both windows. Okay, so now you start this going here. How do you do, let's see.
Mas ele junta cada show lá no trabalho.
Yeah. Okay, so is it everybody working? Is it working for everybody? Do you understand what's happening?
Yes.
So I'm teaching you guys about solve and about Linux a little bit. Tail is a Linux command that says print the end of a file. And if you say tail minus F file name, it will keep on looking at the file, and every time something more is printed, it will output. So I think that's a good place to stop. We come back after lunch, we'll do a solution that has lots of arcs. So it's going to take a fair amount of time. And so we'll combine data from several years.
I have one window with solve and the other window with the tail that we did.
Yeah.
The third window, what I need to do for that, just for let ready when we back.
Pardon?
The third window, what I need to do is that.
Okay, so the third window, what you could do is you could do another run of solve.
Okay.
Yeah.
Same file.
Well, you need to have a different file.
Okay.
I mean, you need to use different initials. You can't say E1, you'd have to say E2.
Okay, so I exactly like.
Yeah, yeah. Okay, I'm done for the online stuff. Go after lunch.